Okay, hear the recording in progress. So, share the screen. Right. So, hope you enjoyed your 3-day weekend. We're finishing very quickly. We only have 4 weeks left. And next week's short because of Thanksgiving anyway, so it's even shorter than 4 weeks actually. Right. So we are just about done with 5.3, and we have 5.4 left for this week. And our next exam is this coming Friday. So usual rules apply. You know the rules by now for the exams. There's only 3 sections. 5.4, 1 to 16, all ALL. That's a mean trick, but I'll try to do as many of the evens as possible. Then after that, we just have one last chapter, and then we're done with the course. Okay, and let's see. Quiz. I emailed you back your quiz results, and I sent the video out over the weekend also. So if you didn't get it, your quiz result, your score, then please let me know right away. Okay, so exam this coming Friday. Then we have some of chapter 6. We only do a small amount of it, 6.3, 3, 4, and 7. Okay, so that'll lead us up to next week. We have Thursday and Friday off for Thanksgiving. And then before you know it, we're done. And please notice the final exam date is Monday, the 13th of December. So we literally have less than a month to go, right? Yeah. 1 month from now, we're finished. Okay, so final exam is Monday, the 13th. Please notice the time is 8:10 to 10:40, not 9:10. We start at 8:10. Now, if you want to join at 9:10, then I'll let you, but I stop at 10:40 for the final exam. Okay. All right, so finish up a little bit of 5.3, get started with some of 5.4. And because I'm sort of ahead, most days this week we'll finish early. That's been the pattern anyway. In which case I'll let you ask questions, and if not, we can just adjourn early for all the days. Okay, so let's get back to where we were. We had to graph some problems at the end of 5.3, so let me knock those off. So 5.3, page 303, sketch the graph of the functions. Okay, then 65, you had one matching question. Let's get that out of the way. Okay, so page 304. The last time I showed it, I didn't have the answers there, but I've given you the answers now. So can't get this thing focused that well. But let's see. To me, the easiest is C, ln negative x. ln negative x is the reflection of ln x across the y-axis. So if you think of the regular natural log function, kind of goes like this. And then if you reflect across the y-axis, you would end up with that. So C is I. Okay, and then the next one I thought I'd talk about was negative ln x plus 1. Okay, so we know ln x, how that looks like. Negative ln x would reflect across the x-axis. It would go something like that. And it got translated 1 unit up, but it still has that same general shape. And none of the others has that kind of shape. So that means Roman numeral 3 is A. And then all you have left are B and D, which look very similar. B and D, they're exactly the same, except there's a 2 here. There's ln x minus 1 minus 1, 2 ln x minus 1 minus 1. So in each case, if you were to plug in 2, right? If you plug in 2, you're taking ln 1, ln 1 is 0 minus 1. So they both go through 2, negative 1. Okay, so 2, negative 1, and 2, negative 1. Okay. But comparing the two, this coefficient of 2 means it should go up faster. Okay, so if I look at this one and this one seems to be going up faster. Right, so that leads me to believe that Roman numeral 2 should be D. And therefore, by elimination, B is IV, Roman numeral 4. Okay, so the answers are 3, 4, 1, and 2, evidently, for this one. Okay. All right, so that's it for that one. Okay, then graphs of these logs. You do want to be somewhat familiar with the basic log function. All log functions tend to look the same. On the bottom of, whoops, 298. And y equals natural log of x goes through the point 1, 0. It makes sense that this goes through 1, 0 because the exponential function goes through 0, 1. But all log functions in general, where the base is bigger than 1, look something like that. And then the ones that we have are just translations and so forth of that. So there's a quick review of what we had. So f of x equals a to the x, exponential function where a is bigger than 1. They all generally look like that, pass through 0, 1. Reflect across the line y equals x. You get the log function. So f inverse of s is log base a of x, where a is bigger than 1. This goes through 0, 1, so this goes through 1, 0. Okay, so for instance, 55, a quick sketch of y equals log base 2 of x minus 3. So log base 2 of x, very roughly, still looks like a general log where the base is bigger than 1, goes through 1, 0. Asymptote is the y-axis. And then you might recall from our translation rules, this will shift 3 units to the right. Again, when I use the word translation here, translate means to move. Okay, we're not using translate as in translating a language, but there's an English definition of translate, which means to move. So I just move 3 units to the right. So for instance, 1, 0 moves over to 4, 0. So all I do is move over here and just graph the same thing. Y equals log base 2 of x minus 3 in green. Okay, and the asymptote, which used to be the y-axis, which has the equation x equals 0, got moved over to x equals 3. So that's the graph that we have right over there. Okay. All right, then let's see, 59, y equals 2 ln x plus 1 minus 3. So I did my progression of this, and remember, I made you do something like that in a quiz. I might make you do something like that in a test also, right? Here's a basic function, and then what happens, right? It got reflected by the x-axis or y-axis, or it got moved left, right, up, or down, or it got stretched because of coefficient, right? Okay, so here's the progression that I got. Start with my ln function, goes to 1, 0. Now, ln x plus 1, shift 1 to the left. So 1, 0 moves over to the origin, 0, 0. So this graph goes like this. And then what happens if I put a coefficient of 2, and then I decided to make a new graph because the picture started to get too cluttered. But I did draw the original ln x plus 1. So there's ln x plus 1. And what's the effect of putting a 2 in front? Well, it goes up twice as fast. So when the y value here somewhere is 1, then here it jumps to 2. But on this side, it goes down steeper. So let's say the y value was -1, the 2 would make it -2. So this is the case where on the right side of the y-axis, the 2 ln x plus 1 goes higher. But once I pass the point where y is 0, it switches, it becomes lower. And so I've got the red one, so higher than the black on this side, but lower on this side. And then I just throw the whole thing down 3 units. So the origin 0, 0 moves down to 0, -3. So here's my final graph. 2 ln x plus 1 minus 3. Okay, so be ready to do that kind of analysis like on the quiz, and I might give you something like that on a test, right? So here's your basic function, ln x, and then you get moved left or right or up or down and shrunk or shrink or reflect across the x-axis or reflect across the y-axis and so on. Okay, and remember, please show all your steps and show all your work. Okay, I can give you partial credit if you say, oh, you just made a small mistake here. I follow your logic, so I can give you most of the credit. Okay, if you don't show me in between steps, I don't follow your logic, then you get the wrong answer. What am I going to do, right? So show me all your work for stuff like that. Okay, 61, I kind of already answered that for the matching problem that we did. Okay, ln negative x. Well, ln x looks like this. ln negative x just reflects across the y-axis. So it goes like this. So here's 1, 0. this would be negative 1, 0. By the way, when you plug in negative 1 here, you have negative, negative 1, which is 1, and ln1 is 0. So this is the graph. Okay, just mention off to the side, the problem's finished, but you might look at this and say, hey, you can't do that. Didn't you already say you're not allowed to take the log of a negative number? That's correct. You cannot take the log of a negative number, but the game you're playing is behind my finger. I need that to be positive, right? Can negative x ever be positive? Yes, if x itself is negative. Okay, so I cannot plug in any positive number here. I cannot plug in 0, but I can plug in negative, because if x is a negative, then I have negative x is negative a negative number, so it becomes positive. So the domain is negative infinity to 0. Okay, so I'm good as long as I plug in a negative quantity right here. So that's what we have. Okay, then finally 63, and then I'm done with the section already. Absolute value of ln x. So here's ln x. Okay, we played this game before. Anything that's already above the x-axis stays the same. So this stays the same in red. That's the same as that. Anything below, well, it's got to go above, so it reflects. So that part right here, I take the mirror image across the x-axis. And so absolute value of ln x looks something like that. And that's what we got. Okay. All right, and I am now done with section 3. And the rest of the week, we just have one more section, 5.4. But they're all word problems. Okay, so 1 to 16 all. They're word problems involving exponential growth and decay. So true, yes, we quote unquote only have one more section, but the bad news is it's a pretty heavy duty section where they're all word problems. Okay, so it's on exponential growth and decay, although you may have had that topic in elementary algebra and intermediate algebra, I should say. Okay, so 5.4. Exponential growth and decay. All right, so we had to do 1 to 16. Let me show you the problems for those of you who don't have the book and aren't getting it. Okay, so page 310. And by the way, you'll get this topic quite a bit more in calculus, so it's a good idea to kind of get a fairly decent understanding of what's going on here. Here's 4. All right, so you have some object which obeys exponential growth or decay, as the case may be. Then based on that prediction, you can say, okay, how much is going to be present after a certain amount of time? Okay. See, we have some money problems. When's my money going to double, triple, that kind of stuff. Okay, 16, top of 16, there we are. Okay, that's it. All right. Here is the basic formula that you have. There are different versions of it, but this is essentially it. Put this on your cheat sheet if you want. A of t is equal to A0 e to the kt. And I don't even know what this all means. Okay, so I'll try to explain it. So 5.4 exponential growth and decay. A of t, like a function, A0 e to the kt. A0 is the initial amount. The 0 is for time 0. Quite often when you do an experiment, like a science experiment, you start at time t equals 0. A of t is the amount after time t. Okay, t is in time. It could be years, days, minutes, or whatever you want. K is a constant. It's either a growth constant or a decay constant, which depends on whatever you happen to be studying. Okay. If K is positive, it's a growth constant. If K is negative, it's a decay constant. Okay. Now, in the book, 305, you could see this. Q of t equals Q0 e to the kt. It's the same equation. A is for amount, Q is for quantity. Sometimes you see N of t equals N0 e to the kt, where N is for number. It's unfortunate they have so many different letters. Sometimes you see P for population, but it's all the same formula. A of t equals A0 e to the kt, or Q of t for quantity, A for amount, Q0 e to the kt. P of t equals P0 e to the kt, population. Okay, so exponential growth or decay. So definitely put this on your cheat sheet. So K is a constant of proportionality. It's either positive or negative, as the case may be. Right? And based on this, you can answer all kinds of questions on this. Now, this is very calculator dependent, so you want to have your calculator handy. And for these kind of problems, we're almost always going to do base E. We're almost never going to do base 10 anymore. Here, so I'll get my calculator working here. So get ready to use this button quite a bit. E to the x ln. You're almost never going to use this right now. Okay. All right, so for today, I'm going to get started with doing some of the evens for you. Okay, so a biology example. Under ideal conditions, a cell of the bacterium Escherichia coli, or E. coli for short, commonly found in human intestines, divides to create 2 cells in approximately 22 minutes. Assume the initial population is 200 cells. Okay, 200 cells. That's my initial amount. 1 becomes 2 every 22 minutes. So this cell divides every 22 minutes. And asks us all this stuff. Find an expression for the number of cells after T hours. Find the number of cells that will be present after 10 hours. When will the population reach 10,000 cells? Okay, so all of these questions can be answered by our analysis. Okay, so you have E. coli in the laboratory, in your biology lab, maybe. Maybe some of you are taking biology. Okay, it happens to divide every 22 minutes. Okay, so you start off with 200. So A0, that's my initial population, so that's 200. Okay, so I start with my formula. 200 goes here. Now, 1 becomes 2. That means the population doubles. Essentially, after 22 minutes, the population goes to 400 because it doubles. If 1 becomes 2, then 200 becomes 400. Okay. So T is the time. So 22 goes here, 200 here, 400 here. Solve for K. So 400 equals 200 e to the k times 22. You just plug everything in. So this is my starting formula. I started off with 200. 22 goes here. It says 22 minutes. The population doubles. Since 1 becomes 2, 200 becomes 400, so 400 goes here. Okay, divide both sides by 200. 2 equals e to the 22k. How do I get rid of the e? Natural log, right? ln e cancel out. ln 2 is 22k divided by 22. So k is natural log of 2 divided by 22, which came out to be about 0.0315. Try to show that in the calculator. ln 2 divided by 22. Natural log of 2 divided by 22, 0.03150669, blah, 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 blah. Okay. That's my K. So I put that back into my original equation. And now here's the way this bacteria grows. A of T, the amount after time T, is 200 e to the 0.0315 T. So based on this, I can predict what happens after a certain amount of time, or I can ask how much time will it take for the bacteria to grow to be a certain number, which is part B and C. All right, so time is all in minutes here. So part B says, how much do we have after 10 minutes? I just plug in 10. I type 200 e to the 0.0315 times 10 and punch it in the calculator. Okay, so 200 second function e to the, I'm going to go 10 times the answer. Okay, and let's see. You got it's about 206 bacteria. It says 200 second function. You did it wrong. 274. It's 274. And you wrote it wrong. 200 e to the 0.315. Yeah, it's 274 instead. Okay, so we have 274 bacteria. Part C. When will this culture grow to 10,000 cells? C, 10,000 cells. So this thing's growing, right? This E. coli is growing. So you can say, at what time would there be 10,000 cells present? So that's the new amount. So 10,000 goes here. 10,000 equals 200 e to the 0.0315 t. I now know the constant is 0.0315. Divide both sides by 200. 50 equals e to the 0.0315 t. How do I get rid of the e? Natural log both sides. Okay. These cancel out. So this ln shows up quite a bit, as you might guess. ln 50 is 0.0315 t. Divide both sides by 0.0315. Punch it in the machine and get my answer. So let me actually just try it. ln 50 divided by 0.0315. So roughly 124 minutes. Or a little bit more than 2 hours if I talk more traditionally. I mean, rarely in common speech do we say 124 minutes, right? With anything bigger than 60 minutes, we say, okay, so many hours. So I would say 2 hours and 4 minutes, or a little bit past 2 hours. Okay, so under these conditions, if you've got this much E. coli in the Petri dish or whatever, right? And you say, how long does it take to get 10,000 cells? A little more than 2 hours, 2 hours and 4 minutes. So this is a typical kind of question that you can get based on exponential growth and decay for these kind of problems. Okay, so that's basically what we have for the rest of the section. All these kind of word problems. Okay. So, 2 more like that. 4, a bacteria culture started with 8,500 bacteria, increased by 15% in the first 2 hours. A, find an expression for the number of bacteria T hours after the culture was first observed. Find the number of bacteria that will be present after 8 hours. When will the population reach 35,000? How long does it take for the population to triple? Okay, so all these questions can be answered. All right, so start off with AFT is A0 e to the KT. The initial amount, he told me, was 8,500. Okay. 8,500 bacteria. That's my A0. Now, it said increase by 15% after 2 hours. So AF2 is 15% more. 15% more means I multiply by 1.15. 8500 times 1.15. 97.75. Okay, you have to watch out for that increase of 15%. You multiply by 1.15, or you can multiply by 0.15, which is 15%, but then you add it to the original. Okay, so we say, well, 8,500 times 0.15, that's 15%, right? 0.15, I'm not supposed to write. Okay, that's 0.15, but you still have to add the original 8,500. So at 8,500, there's a 97.75. Okay, so that's why it's usually faster to just multiply right away by 1.15. Okay, 1.15 times this. So 8,500 times 1.15. That's an increase of 15%. It went up by 15%. Okay, so 97.75 goes here, 8,500 goes here, e to the k times 2. Solve for k. Divide by 8,500. 1.15. No big surprise. That's where we got the 15% increase from. Equals e to the 2k. Time was 2. Take the natural log of both sides. ln 1.15 equals 2k. Divide both sides by 2. Punch it in the machine. So k is this, which is about 0.0699. And let me see if I can show that to you. ln 1.15 divided by 2. 0.06988 rounds off to 0.0699. And once again, those of you that have a calculator that automatically gives you the left paren, close it with the right paren. So some of your calculators automatically goes like that, right? If I can get this thing focused. Then you folks would have to actually close the parentheses like that and then divide by 2. Okay. Make sure you don't do this. Okay, so do not do this. That's going to be different. See that? So there it is. In fact, it comes out to be negative something. So whatever. Okay. All right, so part A is done. 8,500 e to the 0.0699 t. Now part B. Part B, 8 hours. Plug in 8. So plug in t equals 8. A of 8 is 8,500 e to the 0.0699 times 8. Approximately 14,867 bacteria. For bacteria, give whole numbers, right? We don't want to give the answer as a fractional bacteria. So let me type that in for you. 8,500, second function, e to the parentheses. This time you have to put the parentheses, 0.0699 times 8. 14,860, whatever. I guess 14,868. I had 7 at first. Which is what 8. Anyway, let's make it an 8. C. When will the population reach 35,000? That's the new amount. So that 35,000 goes on the left-hand side. So 35,000 equals 8,500 e to the k t. Solve for t. After a while, you do enough of this, you're doing the same stuff. Divide by 8,500. After canceling, I can reduce this fraction to 70 over 17. I divided out the zeros and divide by 5. So 70 over 17 equals e to the 0.0699 t. How do I get rid of e? ln, natural log of both sides. So natural log of 70 over 17 is 0.0699 t. Divide both sides by 0.0699. Put in the calculator. 20.25 hours. Okay, so it's almost a day, almost a full day. And let me type that in for you natural log 70 divided by 17, close parentheses, divided by 0.0699. 20.25, roughly 20 and a quarter. Let's see what I have. ln 70 over 17 divided by 0.0699. Okay, and finally, D. How long does it take for the population to triple? Okay, so sometimes you want to talk about doubling something, tripling something, or cutting something in half. Okay, next time we'll talk about half-life. Okay. And problems involving half-life. So we want to triple. So I triple the original amount. Triple means multiply by 3. 3 times 8,500 is 25,500. 25,500 equals 8,500 e to the 0.0699 t. Divide both sides by 8,500. 3 equals e to the blah, blah, blah. Okay, so after a while, you end up doing the same thing. It's very repetitive. How do I get rid of the e? ln, right? Same old stuff. These guys cross out. ln 3 is 0.0699 t. Divide both sides by 0.0699. Punch it in the machine. 15.72 hours. Okay, so ln 3. I know what I do. Some of you have this backward type of calculator. Let me show that to you. If it's a backward type of calculator, you folks have to hit the 3 and then ln. So let me show you. Hit 3 and then ln. Right. So you're either going to do ln 3 or 3 ln. And then divide by what? 0.0699. So divided by 0.0699 equals, and there it is, 15.7169, blah, blah, blah. Round up to 15.72 hours. Okay, so that's what we're up against in this last section. So only one more section, but it's all word problems. Okay, I'm done for the day. Next time we'll do more of these, and I'll try to do as many evens as possible. But all these word problems, right? So you have this standard exponential decay and growth. A of t equals A0, e to the k t. Try to figure out stuff. What was the initial amount? Right? What's the time? What's the new amount? Figure out the k. Then you can answer all kinds of questions involving this stuff. Okay. All right, I'm done. Let me check the chat. 5.313 is asked for. Let me see if I'm able to do that. Yeah, 5.313. There's really nothing to do. The ln and the e are back to back, so they just immediately cancel, and the answer is just 1/3. Okay, so if the ln and e back to back, they cancel out. Same thing for 11. E, ln, they cancel out, so the answer is just 5. So there's really nothing to do right there. Okay. All right, so any other questions, please? Check the chat. Otherwise, that's about it. Any questions? Otherwise, we're done. So the rest of this week, we'll do more of these kind of word problems. That's essentially all that we have left for this chapter. All right, then I guess that'll do it for today, folks. So have a good day, and we'll see you next time. Okay. All right, bye, everybody. Thank you. Bye, everybody. Thank you.